This conference will now be recorded.
Okay, so let us UCIe protocol demo session. I mean, now the session is at 2:30. So otherwise, from next week onwards, we'll try to have it the regular timings mornings so that it will be comfortable for most of the participants. I'll also check with the participant what time works for them. Accordingly, we can even plan the session. So before we go into the protocol, I will just quickly walk you through the what is the agenda for the 6 weeks training. So during the demo, we'll focus on understanding what is the need for UCIe protocol, and we'll also discuss some of the UCIe keywords, like in what exactly is mean by few keywords which we will very frequently be using throughout this training. What is mean by non-flit mode, flit mode? What is the 68-byte flit mode? And what is 256-byte flit mode? And what is latency optimized flit? So there are few keywords we need to understand. So that we'll focus on. And the week one will be focusing on the UCIe layer stack, protocol stack. That is the protocol layer, the die-to-die adapter layer, the physical layer, and the interfaces like FDI and RDI. That is FDI stands for Flit Aware Die-to-Die Interface. RDI is the raw die-to-die interface. We'll understand what exactly are these interfaces and what are the signals that constitutes these interfaces. Then we'll also discuss about different configurations of the UCIe implementation. Like you can have single module configurations, you can have multi-module configuration where you have got two modules or four modules. So you can have up to two or four modules per configuration. We can also have configuration where there is only sideband. You see, going forward, we'll see that UCI Express link will have two uh, transmission lines. One is the main band transmission, one is the sideband transmission. So we'll discuss what exactly is the main band and sideband. Then we'll also just focus on some of the key performance targets. I mean, what is the bandwidth and what is the power consumption per bit we are targeting? In one, in terms of the bandwidth per square mm, okay, and also the power per per bit. How many picojoules we consume per bit? I mean, what are those targets? Then we'll also talk about how the UCIe has been implemented for interoperability. I mean, how what kind of things need to be accounted in making UCI Express interoperable with other dice. Then we'll, in the next week, following week, we'll be completely going deep into the protocol layer, where we'll understand the different protocols that that UCI Express supports. One is the PCI Express, one is the CXL 256-byte flit mode, 68-byte flit mode, the streaming protocol. We'll also talk about management transport protocol. Then in the following week, we'll be discussing the die-to-die adapter layer, where we'll understand all the aspects of die-to-die adapter layer. And this is where most of the important things happen, because the protocol layer, as it is nothing. I mean, the protocol layer is what we essentially generate the different types of protocol packets. Most of the bit manipulation, the packet reframing, all happens in the die-to-die adapter layer. So as part of that, we'll understand what is stack multiplexing and what is adapter initialization. I mean, what exactly happens during the adapter initialization, how the parameters get exchanged. Then we'll also discuss about the different modes of operation and the protocol and the Flit format and the power management link states and the retry rules. I mean, most of the retry, CRC and retry happens in the die-to-die adapter layer, except for raw format. So we'll also discuss what is raw format, what is Flit specific format. All those we'll discuss. Then we'll also discuss about parity based runtime link testing. Then in the week 4, we'll discuss about physical layer, where we'll talk about logical physical layer. And basically we'll majorly focus on how this physical layer differs from PCI Express. I mean, how this physical layer, rather I would say, how UCI Express physical layer differs from the PCIe and CXL, PCI Express physical layer. Okay, that will give you a lot of clarity actually, because PCI physical layer is quite complex, because we don't have a dedicated separate clock being sent, whereas in UCI Express you have something called as forwarded clock. That eliminates lot of things. Basically, in the UCI Express, the link also has something called as forwarded clock, where clock is sent as a separate lane between transmitter and receiver. Because of that, you don't need to have that complex clock recovery circuit. You don't need to do 8-bit NB encoding is not required because you don't need to extract the clock. I mean, earlier we used to use 8-bit NB encoding in PCI Express, and even the scrambling, lot of things we were doing for clock recovery purpose. So a lot of that can be avoided in UCI Express physical layer. So the physical layer implementation becomes quite simpler because of those things. Then,
Srinivas, I can ask you a question here.
yeah, please. Yeah.
Is it because so the clock is sent in UCIe because the chips are very closely put, and in PCIe it is not sent. I mean, in the it is embedded in the lines. Is it because the distance is more?
Yes,
Is
yes.
it because of that?
Yeah, that is also one major reason, because the chips are dice are tightly coupled. I mean, dice are tightly coupled on the package.
Because of that, so we
So
need to
it
send the clock
leads to
between the chiplets.
the problem of skew won't be there much. The
Okay.
the clock skew will not is not a major problem. Won't be a major problem.
Let us use the word die and then chiplet alternatively so that people are familiar with it. So both are
Yeah,
acceptable. Let's use
yeah,
that. Yeah. Thank you.
sure. And even otherwise, and other than that, anyway, off package connections also can be done using retimers. That also we'll discuss how the retimers will help in one of the following weeks. Then we'll talk about what is data and sideband transmission flow, what are the signals and how they are sent. Then the physical layer is also responsible for lane reversal, and it is also responsible for interconnect redundancy remapping. What is redundancy remapping is, if there is any faulty lane, there is a provision where the UC Express provides some spare lanes, redundant lanes. Those lanes can be reused to remap the faulty lanes. So that is also we'll discuss. Then we'll also discuss about data to clock training and the different test modes. Then we'll talk about how the link initialization and training happens, that link training state machine, and runtime calibration, multi-module links, all those things we'll discuss. Then we'll also focus on some aspects of the electrical physical layer, where we'll talk about all the electrical aspects like transmit spec, receive spec, clocking, the ball out and channel specification, tightly coupled mode. So various things we'll discuss. In the week 5, we'll talk about the UC Express 3D kind of packaging. See, there are three kinds of packaging that are supported in UC Express. One is standard packaging, one is the advanced packaging, one is the UC Express 3D packaging. We will discuss about how the 3D packaging differs and what are the features, and how the transmit and RX and clocking is implemented, and the sideband specific to UCI 3D. And we'll also talk about the UCI Express retimers. Then in the last week of the training, we'll mostly focus on the architecture. That is, here we'll discuss about how the discovery happens of the UCI devices connected to each other. I mean, what are the configuration registers that are present in UCI space, that how it will be detected. I mean, what kind of device, what kind of Flit protocol it supports. All those things we'll discuss as part of this. So there we'll discuss about UCI Express manageability, the memory access protocol, and management transport packet encapsulation, and some debug and test architecture is all what we will be discussing in the final week of the training. So this is a brief about what we plan to cover. So do you have any questions till now?
So is it weekly twice or weekly once?
Weekly twice, Saturday and Sunday we'll have the sessions.
So morning session from tomorrow. I mean, tomorrow we have a session.
And tomorrow we'll have next Saturday onwards we'll have.
Okay, tomorrow is a break, and next Saturday morning session only you are planning. Is that the
Yes,
case?
yes, yes, yes.
Sure.
Yeah. Any other questions you have?
Will you provide any support document for this?
Support document, in sense, I can provide you the one is the presentation. One second. This one. One is the presentation. I'll provide access to that one. Other than that, in case you need, I can provide you the spec as well. Okay, we'll discuss that part. Spec, I think I can provide, that won't be a problem. Okay. Maybe you might have, but I can provide you this presentation document. I'm still working on improvising it. I mean, this is something raw document we have created. Generally, what happens for this kind of complex protocol, over the training period, when I start looking into each week content, I keep updating my presentation. So towards the end of the training, I'll be sharing this updated presentation with you. So any other things? Okay. So first, let's start off with some basic questions. Like, I just want to ask the participants. I think few of you are there. What is your comfort with the PC Express Gen 6? And second is CXL. It could be 2.0 or 3.0. What is your comfort?
I am
Uh,
familiar with Gen 6 Flit Mode 2.
Okay, fine.
CXL, yeah. I think I took training from you, CXL. So you don't ask me. So you don't ask me questions in that. So 1.5 years ago, I took training from you. Don't ask me questions now.
Okay,
I
fine. No,
haven't
no,
done.
no. I just
I
want
haven't
to
done
know
anything.
what is the comfort level of the participant, so that I can cover
I
those
forgot.
basics.
Yeah. Sure. I can understand if you say. Yeah. Don't worry about it. Yeah.
Okay, sure.
And
How about the,
Shantirazu is driving actually. So can you speak Shantirazu, or can you? Are you speaking Shantirazu? We don't hear you. Okay, he's actually driving Srinivas Reddy. So Shantirazu is driving. So he said
okay?
he will be on mute, but he will still be listening to your presentation. So
Okay,
actually, we are friends
that's okay.
actually.
Yeah, I know, I know. So fine. We'll anyway. Let's start off with this session. Okay. I mean to say, irrespective of your prior expertise, let me quickly revise these concepts. Okay. First, let's start off with the question: what is the need for UC Express? Okay. Can someone tell me, based on your prior understanding, what do you think is the need for PCI Express? Sorry, UCI Express. As you know, UCI Express stands
Actually,
for
yeah, yeah. Actually, earlier we had monolithic chiplets only, chips only.
yeah,
But because more and more logic is being packed, a single die solution is not working because of the yield issues. That is one of the issues.
yeah.
And because of that, total logic is divided into multiple dies, and we need to connect those dies, and that
Yeah.
is where the interconnect between the dies. That's what my understanding.
Okay. I would say three reasons, but of course there could be more things that you could add. One is the, like the way you pointed, yield. I mean, as the number of dice are increasing, so if you think of some server chip, I mean something that is targeted for server, or even some dice that are targeted for some AI applications, right? All those things will require a large number of cores. They require large number of cores, and they require a large number of the SoC components for it to work, in terms of the memory, in terms of the accelerators, in terms of the processor cores. So it requires large number of them. That is where the traditional monolithic based chips, what is monolithic? The one in which entire logic is going into single chip, the entire the circuit logic going into single chip. Okay, it is becoming a limitation due to the yield. One is due to the scalability. What is scalability is, for every different configuration, let's say I need different chips, one with 32 cores, another with 64 cores. So I'll have to implement two different SoC flows for that. One I have to take with 32 cores, one I have to take with 64 cores, and then I have to do it as two separate design projects. Okay. Whereas that is where the UCI Express can solve the problem of scalability, where you implement your logic one as a separate chip. This 32 cores or 64 cores as two separate chips. Okay. Then you have one packaging technology where all other components, let's say you GPU, you need some memory, you need some peripheral components, and everything, you interconnect them through some technology called as UC Express. Where here, if you want to use 32 cores package, you use 32 cores chiplet. If you want to use 64 cores chiplet, you can use that. So essentially what it does is it creates a scalable application where you can create the system with as many components as you want, and you can easily mix and match the things. I mean, for example, one more thing it can do is, you may, for your implementation reason, you may use this to be 7 nanometer node. We may implement this to be 5 nanometer node. Some other component could be 7 nanometer mode. So it is all this mix and match is possible, where sometimes you know that there is a some yield issues when I work at lower technology nodes. Rather, I can go for 7 nanometer CPU subsystem chiplet. So it gives me a flexibility where different chiplets or dice can be fabricated at different technology nodes. Okay. And they all can be interconnected through this universal chip level sorry chiplet interconnect, sorry, chiplet interconnect. Okay. And it all can be done seamlessly, where the UCI has been implemented for that specific purpose. What is time to market is indicating here, you just have to, it's like from the shelf you are picking, like it's like as a designer you're telling I need this many CPU cores, you're picking that block. You're telling this kind of GPU I need this kind of memory. So you're just picking them, you're connecting all of them through one common thing. So that also reduces the time to market. So essentially, in terms of the cost, in terms of the yield, in terms of the scalability and time to market, so UCA offers various advantages. So this is the
I
reason
have a
why we are
question
going
here.
for. Yeah,
So let's say you have 4 chiplets,
yeah,
right? So all are
yeah,
connected through UCIe. So
yeah.
do you have any idea in the market where 3 chips are from one vendor and the 4th chip is from a different vendor? Do you have any such idea where a single a package containing multi dice with one of those dice is from a different company and remaining are from different companies too? Because it's a common,
Uh,
right? UCIe is common, right? So is that solution
yes, yes.
right? That's what I want to know.
No, in fact, that is common. But if you ask me which company is doing, I'm not sure. But that is the
Okay.
very purpose of the UC Express.
See, that's what I wanted to know. Yeah. Okay. Okay.
In
Let's not
fact,
name
in
any
fact,
company. Yeah.
yeah. No, it is done. It is done. In fact, UCI Express idea is also that, see, in UCI layer stack, right, protocol stack, as you know, there are three layers are there. One is the protocol layer, one is the D2D die to die adapter, one is the physical layer. Okay. Now, what it also says is that you can pick protocol layer from one vendor, you can have your own die to die adapter layer, you can take physical layer from some other vendor, and you can put together all of them. That is also possible.
Cool. So multi chiplets can be from multiple vendors, and
Yeah,
that is practically it's being done. Okay. Excellent.
it is done, and even this could also be done now. it, it's
Sure.
possible that companies are doing it because for someone may have expertise with the protocol related aspects but may not have expertise with the analog front end analog aspects of the thing, right? They may prefer to get the physical layer from some other vendor. Okay. So in that case, what it does is, between these layers there is something called as FDI. Between these layers there is something called as RDI. So this has also been well defined. I mean, FDI has a fixed set of signals. Means someone who is implementing protocol layer has to implement with the same interface. Someone who is implementing D2D adapter also has to exactly use FDI to interface with protocol layer. So there cannot be any deviation. So you can think of these things to be something similar to DFI, DDR5 interface, which allows someone to implement DDR controller. Some other company can implement the DDR5, and both of them using the DFI as the standard interface. So we can interface DDR controller with the DDR5 through the DFI. Same way, the UC Express gives this FDI and RDI. When we go through the presentation, we'll see that what all signals are there, which signals goes from protocol layer to die, and which signals goes from die to protocol layer. So that signals are also very well defined. So because of that, it is possible to mix and match these layer implementations also from different vendors. Let's now use some terminology. What is mean by monolithic chip? What is mean by chiplet? Okay, I'm sure people are familiar, but still let's talk about. Can someone tell me what exactly we are referring to monolithic chip? Can someone tell me? So monolithic chip is like one single silicon wafer on which entire chip has been implemented. Let me, just for convenience, let me take one SOC diagram as an example. Through that I will explain. So if I say monolithic chip, in this SOC, the entire SOC is being implemented onto one single silicon wafer. So when I fabricate this silicon wafer, you know, right, how this work? In that, in the wafer, you have to just have, sorry, one of this thing represents this entire SOC. That is what we are calling as the monolithic chip. Okay. What is mean by chiplet? In this context, in this diagram context, can you tell me what does chiplet refers to? This diagram context, can you tell me what does chiplet refers to?
Entire SOC is one chiplet.
No, we can actually implement this as one chiplet.
Okay. If you break it down, if it is big, very big, yes, you can then break
Yeah,
it down into chiplets.
it basically gives me flexibility where I can implement every individual thing as a chiplet. Only thing is, when I say chiplet, and I should be able to connect these two, right? One chiplet should be another chiplet. So how do I do that? Okay, now let's say if I manufacture one chiplet as chiplet means what? The individual subsystem. Now subsystem can be the CPU subsystem or accelerators or any CXL devices, any CXL type 1, type 2, 3 devices. They all can be chiplets. Once you have these chiplets can be interfaced using, can be interconnected using UCIe link. Okay. Now the first question comes is, when you are connecting these chiplets, okay, like this, for example, okay, do you think should it be a on chip protocol, or some kind of peripheral protocol?
Not on chip.
It can't be on chip because this is a separate wafer. This is someone has manufactured a separate wafer. This is someone has manufactured a separate wafer. This another wafer. So you are connecting one die with another die. So when you are doing it, it cannot be on chip protocol. It has to be some kind of peripheral protocol. That peripheral protocol is what we are calling as the UC Express. These chiplets are connected using the UC Express link. Okay. That is where technically what UCI Express is doing is, I mean, if you ask what exactly what is UCI is doing is, UCI is uh, doing tunneling of PCI Express or CXL or raw format protocols, packets, protocol information, protocol data, protocol flits or packet, whatever you can call it as. So tunneling means what it does, tunneling in such a way that it does in a very high efficient manner. I mean, in this case, what happens is, if I take the UC Express like this, I was talking about this diagram, right? Let's say this entire thing will call as the protocol layer. Below that, it has got something called as D to D, die to die adapter layer here. Below that, it has got the physical layer. So the protocol layer here, you see it is sending some transaction information here, right? See, this link is the let's assume chai protocol or something, whatever, a chai or AXI protocol, whatever. So uh, first, this die to die adapter layer understands what is the block with which I'm working. I mean, what kind of format is it going to send? There are three major formats that are defined. Okay, one is three major protocol formats that can be implemented in protocol layer, that can be implemented in UCIe protocol layer. One is PCI Express, one is CXL, one is called as raw format. Okay, basically raw format is used where when the protocol is not equal to CXL or PCI Express. I mean, if it is PCI Express or CXL, the format is very well defined. So there is a different way in which UCI Express handles them. If it is raw format, you are just giving raw data. It's like in this case, if you go to this diagram where you have got the die to die adapter layer, this is the protocol layer, this is the physical layer connecting to, let's say it is connecting to GPU subsystem. GPU subsystem also has a protocol layer. It also has die to die adapter layer. It has got a physical layer. So these two physical layers are connected. Now this is what we are calling as the chiplet. This is what we are calling as a chiplet. This entire thing is what we are calling as. So someone who is manufacturing this GPU subsystem using UCIe as a chiplet, they will implement the entire functionality into the protocol layer. They will have die to die adapter layer. They'll have the physical layer. So these physical layer will have a small a few more things, something called a sideband link. One is main link. Okay, and then these here also sideband link, main link, so they will be connected with each other. So like this, various connections could be implemented. Till this point, have you understood what is doing? Okay, so what the die to die adapter layer does is, once you start off the system, there is a some kind of the negotiation happens between die to die adapter layer here and here, where they try to understand their capabilities. So it'll advertise what uh, the protocols do I support, what protocols do I support. So they agree upon specific protocol. For example, in this case, they agree upon raw format. Raw format means that they are not going to either work on PCI Express, they are not going to work on CXL. They're not going to send any CXL data or PCI data. They will be sending some raw data. Now, raw data can be AXI protocol, raw data can be some Ethernet frames, Ethernet related traffic, raw data can be chai protocol traffic, anything. What do they do is, when the traffic comes here, there is something called as 68-byte flit mode. So there is a specific flit mode. It will convert that entire, it will put that entire information into that flit and transmits the data to the physical layer. Any questions?
Srinivas, one question here.
Yeah, yeah,
So when you said the die-to-die layer of one chiplet talks to the other die-to-die layer, right? So is
yeah.
it auto negotiation or somebody has to come and then initiate them? Okay, talk to each other. Is it auto negotiation?
It will be through initiation. I mean, someone has to initiate that, right?
No, in
At
Ethernet,
the
right? It's when you plug in the node, they are auto
yes.
negotiation, right? Similarly,
I,
in this case, die-to-die layers are they auto negotiating or somebody from the higher level layer should tell
no, no,
try to
higher layer will initiate that process.
okay, sure, got it, perfect.
Okay. Yeah. So
It's not auto
I hope.
negotiation then.
Yes. See what happens again, just to draw here, die to die adapter layer, you have got physical layer, die to die adapter layer, physical layer. So they basically negotiate about what is the link width at which they work. See, for example, it can support at, there are different packaging technologies are there. See, one is called as standard packaging, which only supports 8 lanes or 16 lanes. Okay, the advanced packaging, there is another type of packaging where this could be implemented using advanced packaging. They support either 32 lanes or 64 lanes. So accordingly, there is that the way it happens in other protocols, the negotiation happens between at the die-to-die adapter layer, at the physical layer, where they agree upon the link width and the which protocol they are going to work, various format of the packet, everything. And then once that is done, the packet transmission happens. Okay. In this case, in this whole picture, what is the role of UC Express is, if it identifies whatever the protocol layer I am supporting, whatever is the protocol I am supporting, is it capable of CXL, and is it 2.0 CXL, is it 3.0 CXL, is it PCI Express, if at all it is PCI Express, is it a anything before Gen 5, Gen 5 or before Gen 5, or is it Gen 6? So it identifies, or it identifies it's neither CXL nor PCI Express. That means I have to format I have to process a raw format data. So it identifies everything. It converts everything into something called as Flit format and sends it. Okay. Then, as in any other protocol, there is a chance of errors happening, right? There is also a mechanism called as CRC check and retry mechanism, like any in any other protocol. So in summary, what happens is, the die to die D2D adapter layer, why it's called as adapter, it adapts, I mean, it figures out what is the supported protocol, it figures out the protocol supported and negotiates on which protocol to work at. Just give a minute. Yeah, so we'll discuss more about how the die to die adapter level initialization happens, what are the functionalities of die to die adapter as we go forward. So essentially what the UC Express is doing is, it is converting, if I, let's say, from the protocol layer, if I give, assume it is a CXL type 3 device, assume, right, even CPU subsystem can be implemented as type 1 device. In CXL you would be familiar that type 1 device, type 2 device, type 3 device, based on whether it's a cache device, whether it's a .mem device, .io device. So there are few combinations. Assume that it is a CXL type 1 device which supports let's say .cache and .mem. Okay. In that case, what kind of information will it be transmitting? Can you tell me? If you have a CXL type 3 device or type 1 device, what kind of packets will it send? It sends out either 256 byte flit or 68 byte flit, right? One of these things, right? It will either send out 256 byte flit or 68 byte flit. So this is what comes out of the protocol layer of the CXL type 1 device. So after that, other layers won't be coming. So other layers will be replaced with the D2D adapter layer and the UCIe physical layer. So what this die-to-die adapter layer does is, it takes either this 68 byte flit or it takes either 256 byte flit mode. I mean, it knows which one it's going to get, because that negotiation has already happened. Where it knows what kind of flit I'm going to get. Flit means flow control unit. It's a fixed sized, fixed format packet which is sent every time. That means if there is one CXL device, another CXL device, which are working in 256 byte flit mode, that means every time any information I want to send from here to here, it will always be sent as 256 byte flit. The only thing we are here doing is that, instead of putting everything onto a single chip, and connecting them through some PCI Express link, where you are able to send CXL traffic from here to here, here to here, what we are doing is, we are dividing this as a, we are manufacturing as a separate chiplet, manufacturing as a chiplet, separate chiplet, we are adding additional layers like die to die adapter, physical layer, where we are converting that CXL for traffic into something called as UCIe format. There is a small transformation that happens. Then that will be transmitted through the link to the other one. To make the link connectivity simpler, the whole link is divided into two things. One is called as main band link, which carries the main traffic. One is called as sideband link. Sideband link is for power management purpose, any negotiation purpose. Let's say you want to exchange the parameters. I mean, what are my capabilities? What are my capabilities? Those, that kind of information, both chiplets wants to exchange with each other. That entire thing will happen through something called a sideband. The main band is one which actually carries your traffic. So whatever I was telling, right, the 256 byte flit information will be carried Flit. For example, when you are sending these informations, you need to give power management acknowledgement, right? Sometimes you want to do power management, state transitions and everything. That information will be carried through the sideband channel, and also any parameter negotiations that has to happen, that will be done through sideband. So it is done so that the overall link performance will not be impacted, because sometimes if you, while during the traffic, if you start doing some sideband activities, the main band link will get impacted, right? So for that, they have purposefully divided this into two things. Now also, the fact that you are implementing as two separate chiplets, then what can happen, some lanes may get damaged. For example, to provision for that, to take a provision for that, the UCI has allotted some spare lanes. Let's say they may have allotted 4 spare lanes, which can be used for repair purpose. For example, this black lane is not working fine. So you can reconnect, readjust, remap the things and use that spare lanes to correct the faulty lanes connection. So this kind of convenience is what UCI Express is providing. So this is a brief about why we are talking about UCI Express and how UCI Express makes the chiplet connectivity easier. So if you have any questions, we can discuss. Otherwise, we'll move on with the presentation now.
Sriram said one question, one point
Yeah,
actually. So when
yeah,
we started off, we were only four. Now so many joined, right? So you may
yeah.
want to ask their PCIe and CXL experience or knowledge, and based on that, you can create appropriate slides for it.
Sure,
Then
sure.
we
I'll do that.
actually,
Yeah, yeah.
please, thank you.
Yeah. So those people who have just joined, right? Initially, we started off with just asking the participants what is their comfort with PCI Express Gen 6 and CXL 2.0, 3.0. Can someone, I mean, can you please tell me what is your comfort? How much, I mean, to what extent you know PCI Express and to what extent you know CXL? You can say if you you can give a frank answer, because I don't expect you to be expert with these things, and even
Sir,
expertise is not required.
sir, I am not aware of PCI. Like, I have not worked on PCI and I have not gone through even Excel
CXL.
also.
Okay. What about other participants?
Yes, same Srinivas. I don't know either PCI or CXL.
Same
Okay,
goes with
fine.
me.
Yeah, same goes with me as well.
Okay, fine. So fine. Let me just then explain you some basics. But if you ask me how much basics you know, I mean, the question is how much of PCI Express and CXL do we need to know? Are the prerequisites? Are the UCIe course prerequisites? Let's first discuss that. Okay. I would say around 20 to 30% of these protocols. Now, what is that you need to know? Let's understand what is the 20 to 30%. You should be knowing the standard 68 byte Flit format in CXL, 256 byte Flit format in CXL and PCI Express, and something called as 256 byte latency optimized Flit format in CXL. This is the basic knowledge required. Other than that, there is something called as VLSM state machine. Okay, what is that you need to know? Those things I'll be teaching from scratch, because they need to be covered in CXL. You need to know something called as arbitration and mux logic in CXL. That also will be covered in this UCI training. Okay. And other than that, the UCIe physical layer implementation is quite different. CXL or PCI Express, right? CXL anyway uses the PCI Express physical layer only. So the PCI Express physical layer and UCI physical layer are completely different. The whole difference comes because the UCIe has uses a forwarded clock in the link. So can you tell me what is meant by forwarded clock? UCI Express uses forwarded clock. It means what? If you talk about this as one chiplet, I hope by now everyone understood chiplet. This means, let's say you may buy Intel fabricated chiplet. Okay, you may buy GPU fabricated by Nvidia. You may buy DSP fabricated by Qualcomm. So they will sell as their chiplet. Okay, they will give you UCIe interface. The GPU Nvidia will give you GPU UCIe interface. The Qualcomm will give you UCI interface. They will sell as a separate chiplets. Okay, all of them will be supporting with UCI Express. You just have to know what kind of chiplet. Manikanta, you are not audible. Okay. What you need to do is, as a architect who is setting up your design, you need to ask what kind of chiplet I want from Intel, what kind of chiplet I want to take from Nvidia. Like that, for every block, you can. This is what we should be happening in the future going forward. Okay, where you get the chiplets from different vendors, and you just put together everything and set up your system.
I have a question here, once.
Yeah.
So you mentioned there is a main band, there is a side band, right? Do
Yes.
they carry separate clocks?
Yes, they carry separate clock, because the
Excellent.
sideband will carry 800 megahertz clock. The main band will carry 3.2 gigahertz clock. Different clock frequencies they work at.
Excellent. Okay. Thank you.
I hope you all got. Now, why you don't need expertise of PCI Express and CXL is because the UCI Express, it is mostly it is majorly protocol agnostic. What do you mean by that? Agnostic is, it doesn't bother, much about it. I mean, for example, CXL, you may do something called as host to device request, D2 host request. Okay, some host to device response. So the UCI really doesn't bother about all these things. It only bothers about what is that it is carrying. It doesn't bother about what information it is carrying. It only bothers about that I am connected with a device who will be giving me CXL 68 byte flit. Rather, it will bother about I'm connected with a device which is going to give me 256 byte flit, or I'm going to connect with a device which is neither CXL nor PCI Express. It is raw format. That means I should neither use CXL, I should neither use PCI Express. So it only bothers that much. It won't bother what is there at the next level. If I show you CXL, right, I'll just give you one CXL diagram also, so that you can understand that context as well. Just give a minute. I will also explain you what is meant by flit mode. Okay, it is not a very complex thing. We'll discuss that part. Okay. You see, this is what kind of format? Can you tell me? This is a flit mode where you have got how many bytes are there? 16 bytes are there. This is one type of request. So the point is somewhere I'll show you how the overall flit will look like. Yeah, this is an example of uh, byte flit. This is an example of two. There are two flit formats are there: 68 byte flit, 256 byte flit. That means if you take aside UCI Express, if you take aside UCI Express, assume that this is one CXL device, this another CXL device. They first negotiate whether they are going to work in 68 byte flit mode or they are going to work in 256 byte flit mode. Okay, then they are connected through PCI Express link. See, for CXL, the physical connection is PCI Express only. So again, understand this statement. This is very important. When we are talking about CXL, even though it's a one separate protocol, the CXL is implemented on top of PCI Express. That means you are essentially connecting them through PCI Express link only. So that PCI Express link will either carry 68 byte traffic or 256 byte flit traffic. Okay, when the other side receives the traffic, it it knows what format this 68 byte will come. See, there is a specific format in which these things have been defined, that there will be a flit header, there will be header slot, there will be a generic slot. So there is like that, it has been very well defined. Okay, you see here, flit header will have some 4 bytes. Okay, then header slot is 16 bytes, another generic slot, generic slot, generic slot. Totally it is adding to how many bytes? 68 bytes. Okay, like that, the receiving node, receiving CXL device knows that initial 4 bytes will be flit header, next will be header slot. So what I was telling about UC Express is that UC Express only bothers about that, am I going to get 68 byte flit or am I going to get 256 byte flit? And it knows, if I'm going to get a 68 byte flit, it knows that who is going to get this? The D2D adapter will get. See, from the protocol layer, from the protocol layer, from the protocol layer, the D2D adapter layer gets either of these things. Either it will get 68 byte flit CXL, 68 byte flit PCIe non-flit mode, that is Gen 1 to Gen 5 traffic, Gen 5 flit information. Okay, non-flit mode thing, or it is going to get 256 CXL 256 byte flit, or CXL PCI Express 256 byte flit, and CXL latency optimized flit, or last format is called as raw format. So that means the die adapter layer can get any of these 6 formats from the protocol layer. If it is a CXL device, see, let's say you're talking about CXL device. Now CXL can be two types, either CXL 1.0 or 2.0, or the other one can be CXL 3.0. As you are aware, till 1.0 2.0 we used to use 68 byte flit format. Okay, 3.0 introduces 256 byte flit format. Okay, so during the discovery, during the device discovery, during the UCIe device discovery, Discovery means what? Enumeration. Okay, enumeration. Both the devices knows, both the devices exchange, both the devices means uh, at the devices at D2D layer exchange, the adapter layer exchange this information, and they know which type of flit is going to be exchanged. If it is they know, right, whether my protocol layer is CXL 1.0 or my protocol layer is CXL 2.0. That means I know that I have to work on CXL 68 byte flit format or CXL 256 byte flit format. Let's say we are talking about my device is PCI Express, neither not a CXL. I know that it is what? It is either PCI Express Gen 1 to Gen 5. That means what? In Gen 1 to Gen 5, there is no concept called as flit. It is refers to non-flit mode. Okay. Otherwise, so this will be used. This will be sent as 68 byte flit only. Okay. Now PCI Express can be another type. What is that? It can be PCI Express Gen 6. If it is Gen 6, it will be flit mode. Okay, or it can also be non-flit mode. If it is flit mode, it will be 256 byte flit mode. Flit format will be used. Okay, and in CXL also there is a concept called as there is a possibility of CXL 256 byte latency optimized flit. What is latency optimized flit? Is simple. You're sending 256, you will send us two chunks of 128 plus 128 bytes. You'll send us two separate things so that my receiving device don't have to wait for entire 256 bytes to process the things. It can first process and get all the information of 128 byte. So it doesn't have to wait for entire flit to come. So here itself it has its own dedicated CRC. It has its own dedicated CRC. So hence you are able to optimize the processing. So you don't have to wait for entire 256 bytes to process. You can process half of it and get the information. You can process half of it and get the information. Okay. Or the third could be what? None of neither PCI Express or CXL. Then that is called as raw format. So this kind of negotiation happens during the link initialization and all that. Once they agree upon, what happens is, let's assume they agree upon 68 byte flit format. Let's assume, okay, this my protocol layer is not going to give entire thing. It is going to not give CRC. It is only going to give 64 byte information. It is only going to give 64 byte information. Okay, to whom my protocol layer is going to give 64 bytes to the die-to-die adapter layer. Die-to-die adapter layer adds plus 2 bytes for header plus 2 bytes for CRC. Yeah, both PCI Express and everything will use the same die-to-die adapter layer. Die-to-die adapter layer will be same. That is why it is called as adapter. It's like it adapts to any protocol. It can be PCI Express protocol, it can be CXL protocol, it can be raw format. It will adapt to every protocol. Okay, so what is it doing? The die-to-die adapter layer is taking die-to-die layer. I would say layer. You read it as die-to-die adapter layer is getting flit from the protocol layer. Okay, and it is doing some transformation. What is transformation? Putting it into the UCIe flit format.
One question,
Yeah,
Srinivas.
please ask. Yeah.
So, is there any minimum things the die-to-die layer needs to support? Like, let's say any PCI device should support Gen 1, something like that, right? So, is there any mandatory thing for the die-to-die layer adapter to support minimum things?
Minimum things. I understand that it should support all the modes because I haven't seen a scenario where there is any minimum requirement, but I can check and get back on this.
Sure. Thank
Can
you.
you do one help to me, please? Can you write
Go
down
ahead.
this question at your end, and towards the end of the session, I will take, and then in the next session, I can come back with
I'll type it
clarification.
in chat. Right away. Right away.
Yeah, please, please. Yeah. Okay.
Thank you.
And it is doing some. What is my day-to-day adapter layer is doing is it is transforming whatever information it comes from the protocol layer into UCI Express Flit format. So it does in such a way that see the if you talk about CXL 3.0 Flit or even PCI Express Gen 6 Flit format, it had lot of provision for error corrections. I mean, it provisions lot of fields for error correction. Okay, you know how many? 8 bytes of CRC out of out of 256 bytes of Flit. 8 bytes are for CRC checking, and 6 bytes are for forward error correction. Okay, coming to UC Express, UC Express works at a much higher, in a much better scenario where the bit error rates are very less. Bit error rates are very less. Hence, they purposefully remove this many CRCs. They don't use those many CRCs. In fact, when I get the Flit, when I get the information, I don't even get the CRC. I don't even get the CRC. I get only part of this information. I mean, this of course I will get. Okay. So in that case, what happens is the UCIe utilizes the space even better actually. I mean, whatever Flit you want to send, you don't have to send all these 8 bytes of CRC, all this 6 bytes of FEC. So the UCIe protocol efficiency is better than even CXL. That is because the way the chiplets are connected, right? They are connected. They are tightly coupled. They are tightly coupled. Rather than if you take a PCI Express, right? You may be connecting through a longer this thing. I don't know what is called as the connection from one thing to one part to another part. The connection could be longer to provision for that. I mean, when there is a long connection, right, there's a provision for some failures, right, some error rate to happen. Whereas if you talk about the the chiplets we are talking about, they are tightly coupled on a package, so the length will be, the connection length will be much smaller. Given all that, bit error rate is very less. How much bit error rate they target is they're talking about bit error rate of almost 1 in 2 1 out of 10 to the power of 26, whereas the PCI Express bit error rate target is 1 out of 10 to the power of 12. Okay, that means the UCI Express expects very less bit error rate because of the tightly coupled nature of the circuitry. Hence, they don't provision so many bits for this thing, error correction and CRC. They use less number of bits. That means large number of 256 bytes are 250 large number of bytes out of 256 bytes are effectively utilized. Okay, let's put together everything what is happening here. See, this is the UCI Express protocol stack. The UCI Express, let's say I am a company, okay, who manufactures CPU subsystems. So what will I do? I will manufacture my CPU subsystem. I want to implement it as a chiplet. So what do I do? In my this thing, all my protocol related aspects. What is my protocol related aspects? The CPU core, everything. That entire thing will be part of the protocol layer. Okay. Then along with that, I introduce something called as die-to-die adapter. I introduce something called as physical layer, and there is a FDI which connects protocol layer to the die-to-die adapter. There is a RDI, raw die-to-die interface, okay, which connects die-to-die adapter to the physical layer. and we are connecting, we are putting together everything into one thing, what we are calling as the UCI Express node, or you can call UCI Express device. Let's call it as device. And I can sell this device, and my end user can come with their own requirement, how many cores they want. I can give one chiplet for them. Some other user comes saying that I need 32 cores in this chiplet. I can have a protocol layer with 32 cores. Someone else comes with different number of cores, different cache, various things. So that kind of flexibility I have, where I can manufacture the chiplets as per my requirement and sell. So the other user can just take this chiplet, he plugs it into his UCIe topology, I mean the SOC topology, and can use it. Now coming back to how the protocol works is, as I said, there are 5 formats you can see here. 256 byte flit, that is PCI Express, CXL 3.0, CXL 2.0, streaming. So it has to be one of them. Protocol layer has to be one of them. What is one of them? It has to be either CXL, it has to be either PCI Express. If it is neither CXL nor PCI Express, it is called as streaming protocol, that is called as raw format. One of them will be sent on this FDA interface to the D2D adapter. What is this D2D adapter does is, it does the protocol arbitration and muxing. I mean, it arbitrates, okay, it also does CRC and retry. I mean, if at all some failure happens, it is the die-to-die adapter layer which is responsible for reliable delivery of the flit information. So if there is any error, it will get a retry and it can retry the information again. Okay. Then it also does the link management. I mean, what is the supported protocol, everything it does. And it also negotiates, does the parameter negotiation. Okay. Then it, whatever information it has, it gives it to RDI. See, RDI doesn't have any functionality information. It is only the link level setup and everything. That is link initialization, link training. You know, right? In PCI Express, we have LTSSM, where it goes through detect, polling, configuration, and L0. Something similar we have state machine here also. Then it has got various power states. That is for making the UCI Express more power efficient. Then lane mapping and remapping happens. What is remapping? If there is any lane that got damaged, so that can be remapped to some spare lanes. Scrambling is done, lane reversal is done. You see, we are not using encoding. Can you tell me why we are not using encoding? What is encoding I am referring to? 8 bit 10b encoding, 128b by 130b encoding. What is that basically? It is not required because, can someone tell why they are not required?
Parallel bus, right? We are sending the parallel bus. So
Yeah,
it's
parallel bus. Yes, the basically the nature of communication itself is parallel bus. You have a, actually you have a, if this is another CXL device, if this is another, sorry, UCI Express device, you are sending dedicated clock also, and then you are sending your data. Because of that, you don't need any complex clock recovery circuit and all that. So because of that, my physical layer implementation becomes very simple compared to other complex protocols like PCI Express and CXL. So UCI Express physical layer is much more simpler than other protocols.
why are you not showing main band also along with sideband? One more box needs to
Uh,
be there, right?
no, it is not shown. It is there. Main band is there actually.
Yeah, I think probably you might want to update the picture so next time. Yeah, sure.
Sure, sure. I'll do that. Yeah, definitely. Now, let's talk a brief about what is meant by this flit, because most of the participants, as I see, they are new to this term flit. Let's briefly talk about what is flit. Okay. See, what exactly is the flit is in PCI Express Gen 6. Tell me, what is the data transfer rate we are talking about? 64 giga transfers per second. But the PCI group will be there, right? Wanted to do this 64 giga transfers per second without doubling the clock frequency. They didn't want to double the clock frequency from Gen 5 to Gen 6. They want to use the same clock, use same clock frequency, but get double data rate. So what did they do? They moved from NRZ to PAM4 encoding style. Okay, PAM4 signaling. I mean, in Gen 5 we used NRZ, non-return to zero. In Gen 6, what is PAM4 signaling is basically, if I draw this as my voltage level like this, for example, at this point, if I have to capture, so they divide the voltage level into 4 possible values: 0 0, 0 1, 1 1, 1 0. Okay, in NRZ it's only 2 voltage levels. It's either 0, it's either 1. Whereas at any point, if I sample, let's say if I sample this here, let's say, tell me what is the voltage level here?
01.
0. Whereas if I sample here, what is the voltage level? 1 1. That means in single voltage we are able to send 2 bits with PAM4 encoding, with PAM4, with same single voltage level we are able to send double the bits, double the number of bits. So that way you don't need to, you still do the transition. See, my voltage transitions will still work at 32 gigahertz only. But since you are able to sample 2 bits, now instead of treating it as 0, you will get it as 0 0. This, instead of treating it as 1, you will treat it as 0 1. This will be treated as 1 0. So that way you are able to get more, double the bandwidth with same clock. But it comes with some problem. Because of this, the PAM4 encoding, PAM4 signaling has more noise automatically, right? Because sampling becomes very, I mean, you are sampling the same voltage level in same voltage in 4 possible levels. It worsens the signal to noise ratio. Means there is something called as signal to noise ratio. Because of that, the bit error rate gets impacted significantly. How much gets impacted? It becomes 1 out of 10 to the power of 6. Means in Gen 5 it was 1 out of 10 to the power of 6. What is meant by bit error rate? Means we expect one error to happen out of 10 to the power of 12 bits here. Sorry, it is 12 bits. Okay, that means out of 1 trillion bits you transmit, you expect one error to happen. In Gen 6, 1 out of 10 to the power of 6, we expect one error to happen out of 10 to the power of 6 bits. So there is a very high chance of error happening. There is a very high chance of Gen 6 going through the error. So to mitigate that, what they have done, they added something called as forward error correction code. What is that forward error correction code? Is some additional bits we are sending, additional bytes sent along with the data, along with the packet info, to correct any errors. If any error happens, they will be corrected through this forward error correction code. Got it, right? So along with that, they have kept 8 bytes of CRC. Now the requirement of FEC is, if FEC forward error correction code will work You might have heard some algorithms like read Solomon, uh, error correction code, ECC, some techniques like that. In this case, they use read Solomon forward error correction code. Works only on a fixed size packets. The packets need to be fixed. Only then this forward error correction code works. That is where these people when they develop Gen 6, they had to use a fixed size packet that will be sent. All information will be sent using a fixed size packet from transmitter to receiver. That is what we are calling as the Flit. Flit is always 256 bytes in PCI Express Gen 6. It has got a specific format. Uh, the format is something like this. If this is my 256 bytes, okay, there will be 236 bytes of TLP information, 6 bytes of DLP information, data link layer packet information, okay, and 6 bytes of forward error correction code, 8 bytes of CRC. Can you add all the numbers? 36 plus 6 plus 8, it will come to 256 bytes, and it is fixed. Now this TLPs can be multiple TLPs. It can be multiple TLPs. But the good thing about UC Express is you don't need to bother what will be present inside DLP, what will be present inside each TLP. You don't bother, because the die-to-die adapter layer doesn't bother how my protocol layer will create the packets, what kind of request it is creating, what kind of packet is it. Is it a memory read, is it a memory write, is it IO write? It doesn't bother about. See, the role of the UCI stack is simple. I have manufactured one chiplet, there is another chiplet is manufactured. My goal is simple. Whatever Flit I got, let's say I got 256 byte Flit, for example, from here. My goal is simple. That 256 byte Flit should be delivered to the other chiplet protocol layer. Now that will in turn extract the information and process. It's like simply you're establishing a dotted connection between this protocol layer and this protocol layer. In between, die to die adapter layer is making sure that it it adopts whether I'm sending CXL, whether I'm sending PCI. Accordingly, it adopts and sends the information. It also makes sure that if there is any error happens in the transmission, it recovers. So it is essentially playing the role of a data link layer in the PCI Express. Now I hope you have understood what is 256 byte Flit. And talking about 68 byte Flit, the CXL was one step ahead. Okay, what CXL did is, even before this was introduced, in their 2.0, they have already introduced something called as 68 byte Flit format, where they have defined this fixed format. If you go back here, they have defined this kind of format, where you see first they are going to send Flit header, then they are going to send something called as header slot, generic slot, generic slot, generic slot. For entire thing, they are going to send CRC. So that means one CXL 2.0 device, one CXL 2.0 device. When you connect, the information always goes as 68 byte Flit, always. And that has got this kind of format. Now there could be different formats. For example, you could have one format where everything is data only. See, you see the difference. In one case, header slot, 3 generic slots. You have another case where 4 are data slots, 1 is CRC slot. CRC is always there. Like that, they have given clear description. But as I said before, the UCI Express really doesn't bother about what is there inside it. What is the opcode? What is this mem operation? What is meta value? It doesn't bother. That makes our understanding of UCI Express very easy. You understand that why it becomes very easy? Because as a die-to-die adapter, I am agnostic to what is contained in the CXL Flit, what is contained in PCI Express Flit, what is that I'm going to stream. I don't bother. My goal is simple. I'm going to get something. I have to just deliver it. Okay, now let's go over any questions you have before we start with our presentation further. Any questions you have? Srinivas, you had some question earlier.
I asked it actually. I think Sandeep has latest question. My question was adapter layer, right? So does it need to support minimum formats or protocols? Right? You said next week we will try. Is that the same thing?
Oh, okay, fine. I'll do that. I'll cover that in next week.
And
Let's take.
yeah, Sandeep asked a question. Sandeep asked a question in the chat.
No, for a die-to-die adapter, UCI Express won't use FEC. Won't use FEC at all. The FEC is used only if you are doing PCI Express level connection. PCI Express level connection. Physical PCI Express physical connection. If protocols are connected, if the chiplets are connected using UCI Express link, but with PCIe stack, PCIe protocol stack, okay, protocol layer, protocol stack, they don't need FEC. FEC is redundant. Sandeep, is it clear to you? Now let's do one thing. Let's go through the presentation. Okay, it's a long presentation, around 1700 slides, but I try to optimize it. I'll try to optimize it because it has got a lot of content which we have put as a redundant thing, so I'll be updating it. So I hope to reduce this slide as we go forward. Okay, let's start with the introduction of the protocol. So basically, the UCI Express is a open standard for connecting the chiplets. Now I'm sure you understand what does it mean by. What is open standard is anyone can develop their chiplets using that UCIe protocol. So there is no licensing required. Okay, chiplets are nothing but modular pieces of the SoC. On package interconnect standard. It's a UCI Express is on package. You are on the same package. You are doing the interconnection for connecting multiple dies on the same package. It enables vibrant ecosystem. Means what is vibrant ecosystem is anyone can develop anything and you can just take the package dice from different vendors and just use them. Okay, supporting disaggregated die architecture which can be interconnected using UCI Express. UCI Express supports multiple protocols. I'm sure now you understand what is it mean by this thing. It either supports PCI Express, CXL, streaming, raw format that can be used to map any protocol. The raw format can be used with any protocol. You can use even for AXI protocol, CHI protocol, Ethernet protocol, anything, as long as both ends should support it. If I'm sending AXI traffic, other end should support AXI traffic, right? On top of the common physical and link layer. Next. It encompasses elements needed for SOC construction, such as the application layer, as well as form factors relevant to the package. You see, UCI Express is not the only chiplet connection standard, on package chiplet connection standard. There have been other kind of protocols as well. One is called as OIF, which stands for Open Interface Forum. Okay, that is a XSR standard. That standard is called as, that alliance name is called as Open Interface Forum. Like we have UCIe Forum, a group of companies which have that interconnection standard. There was one more forum called as OIF. They have developed a standard called as XSR. It gives a data rate of 112 giga or 224 giga. Protocol not defined. The package types 2D. It can be used. There is no specific protocol. Package type is only 2D, and it is used for optional networking. Okay, CPO and NPO. Like that, there was one more thing called as Open Compute Project, which uses BOW OHBI, so which has got these kind of factors. Okay. Other than that, you have Chips Alliance, which is standard is called as AIB. Data rate is 6 giga transfers, 6 gigabit transfers. The protocol is not defined. A package type is bridge type of packaging, and it uses military aerospace ecosystem. And the last one is the UC Express. So this is where there is a lot of companies which are adopting this kind of chiplet interconnection. That is where it is gaining the traction. Okay. It supports streaming, PCI Express, and CXL. Okay. This is the protocol stack we have discussed about, and as I have told you earlier, this has been very well defined. Even this has been very well defined. That means anyone who develops protocol layer has to implement FDI. They cannot deviate. Anyone who implements die-to-die adapter layer, they must implement FDI as a separate interface, RDI as a separate interface with a fixed set of signals. So I know that if I'm die-to-die adapter layer I'm developing, I can just procure physical layer from any other company and protocol layer from any other company, and I can just interface everything, and I can create my own UCIe chiplet. So the next, what is the link connection using main band and sideband? This is how it looks like. Please take a look at this ones. You see, you've got two bands, main band, sideband. Main band working at 16 gigabits per second, sideband working at 800 megahertz clock. The sideband has a data that you are sending, and you are sending sideband clock, and see sideband data, sideband clock. See, two clocks are going. One is clock going from transmitter to receiver here, another from here to here. Okay. Similarly, you have got main band where you have got 64 bit data, two clocks, one valid, one track. Again, same reverse connection. Okay. So this how it's been clearly defined. Uh, some packaging options are there. One is called as advanced packaging, one is called as standard packaging, one is called as UCIe 3D packaging. If you talk about packaging options, from advanced package, data rate expected is 16 gigabits per second. Standard package is also this one. The pins per module, the number of pins per module is 64 in case of advanced packaging. Standard packaging is only 16. Redundancy means what? Can you tell me what is redundancy referring to here? What does redundancy refers to in this case? Remapping. Redundancy means in advanced packaging, they have a provision, they have given some additional spare pins for correction purpose. I mean, for fixing the faulty pins. Let's say here, I'll tell you, go back to this example. I know that one of this data lane is faulty. So there will be some additional spare lanes will be there. 4 lanes will be there. You can remap it to this one and use that. So that way, even if it is faulty, you don't need to throw it off. You can use the spare. Like that, there is a specific number of spare lanes that are provided. In standard packaging, it is not provided. The total bandwidth, bidirectional bandwidth, you can get up to 4 terabytes per second. I mean, you can see how big, how large number it is. And here you can get 1 terabyte per second. Sorry, 1 terabit per second, 4 terabit per second. It's simple. The calculation is simple. You take this number, you'll get it. Okay. You can even do the calculation once. We can do the calculation once. We are doing 16 gigabits per second into 16 pins into 2. Let's do. Uh, uh, right. 16 gigabits per second into 16 pins into 2. 2 means bidirectional. 256, 512 terabits it will come. Okay. Bidirectional, only we need to understand how it is coming to 1 terabits. I will let me check and come back on this one exactly how that one is coming. It should be actually 512 gigabits per second, which will be zero point 0.5 terabits per second. I will check and get back on that exact calculation. And the bandwidth efficiency is basically the advanced packaging gives 5.2 terabits per second per millimeter. The standard packaging gives zero point 0.9 terabits per second per millimeter, square millimeter. Okay. uh, Energy efficiency is advanced packaging consumes only zero point 0.3 picojoules per bit transmission, whereas standard packaging uses zero point 0.5 picojoules per bit. Latency is 12 unit intervals in both standard and this one. Bit error rate is 1 out of 10 to the power of minus 15, here 1 out of 10 to the power of 27. Bump pitch is 45 micrometer. I mean the gap between one pin and other pin is 45 micrometer. Here it is 110 micrometer. Channel reach is greater than 2 millimeter. It is greater than 10 millimeter, and it supports idle mode, and termination resistance is not used in advanced package. In standard package, it is 50 ohms. Signal swing is zero point 0.4 in both the cases. This is a comparison between advanced and standard packaging. What exactly is standard and advanced packaging? Let's understand as we go forward. And let's now briefly talk about what are the protocol mappings that are supported in UC Express. As you know, protocol mapped are PCI Express, CXL, and streaming protocols. The mapping for all protocols are done using the Flit format, using the raw format. See, anything you do, whether you are sending PCI Express, whether you are sending CXL streaming, finally my UC Express converts everything into Flit format only. And the UC Express gives a clear definition of how the Flit format will look like. I mean, where the header will be there, where the Flit information will be there, where the CRC will be there. It is clearly defined as in any other protocol they will do, right? Next. Both PCI Express and CXL are widely used. These protocol mappings will enable more on-package integration by replacing PCI Express SerDes PHY and PCI Express CXL logic PHY, along with the link level retry with UCIe adapter and PHY to improve the power and performance characteristic. See, what is happening is uh, these are widely used. These protocol mappings, when you map these protocols to the UC Express, it will see, I told you, right? Only the protocol stack will be PCI Express and CXL, but other layers like die to die adapter and the physical layer will be of UC Express. So you are going to replace PCI Express SerDes PHY, logic PHY, all those things with UCI adapter and PHY to improve it improves the power and performance characteristics. And UCI Express provisions for streaming protocols to also leverage the link level retry of the UCI adapter. See, even in streaming protocols, there is a link level retry that happens in UCI adapter. This can also be used to enable reliable transport of the protocols other than PCI Express and CXL. Even when you are streaming other protocols, there is a link level retry concept can be used for any error corrections, any retries. Okay, let's briefly talk about what is meant by raw format here. Raw means what? It's neither CXL or neither PCI Express. UCI Express also supports a raw format. That is protocol agnostic. What is meant by protocol agnostic? It doesn't bother what is that it's transmitting, to enable other protocols to be mapped while allowing uses such as integrating standalone SerDes transceiver tile on the package. When using raw format, the protocol layer is responsible for reliable transfer of the across the UCI Express link. I mean, the responsibility of the retry lies with the protocol layer in that case. So what exactly is retry, how it does, well, let's discuss. When we go to the raw format, I'll explain you how does that raw format looks like. Let me take one of the questions. Please read this question once. Would someone like to answer this question? For raw protocols like AX, does the D2D adapter need to implement transaction and link layer? Not required.
I don't think so.
Okay. Basically, for raw protocols, you know what happens? The D2D adapter layer has no functionality. Works in cut-through mode. Means it doesn't do anything. It just forwards the flit information as it is. Means any correct error happens, it is the responsibility of the, if it is raw format, right? What happens is it just forwards it. It doesn't do any changes with that. Only if it is CXL PCI Express, it modifies, then modified things it transmits. Sandeep, I hope it answers your question. Similarly, accelerator or IO tile. See, what is accelerator IO tile we are talking about is, I was telling you, right? CXL has different types of devices, type 1 device, type 2 device, type 3 device. So one of them is accelerator type, one of them is IO kind of device. That's what they're calling as the tile. Can use CXL transactions over UC Express when connected to the CPU, leveraging the IO coherency and protocols of the CXL. That means what? I can have the CPU implemented using UCI Express. I can have accelerator implemented as UCI Express. I can have IO implemented as UCI Express. They are all connected using UCIe. So I don't need to use the PCI Express link. I can connect all of them through UCIe. That still gives me a lot of power efficiency and performance also. So it is telling how it all can be done. Means what? When you are connecting through CPU, it can use raw format in case also. The IO tile can provide the Ethernet external CXL, PCI Express and DDR pins of the package. Okay. Accelerator, see, it can even see it is able to connect DDR pins also. Okay. The accelerator can also use PCI Express transactions or UCI Express when connected to the CPU. It indicates that essentially lot of formats are supported. One if you want CXL, one if you want PCI Express. If you want any other raw packaging also can be done. The CPU to CPU connectivity on package can also use UCI Express interconnect running the coherency protocol. So many things could be done. I mean, you can have one CPU protocol which is working on CHI protocol, another CPU which is working on CHI protocol. Earlier we used to use cache coherency interconnect. It is telling that you could still use UCIe and you could have one layer of coherency protocol which of coherency between these things. So all that is possible is what telling us. I mean, that is what UCI Express supports. Next. This shows the diagram example where a package composing of CPU dice, okay, uh, the accelerator dice and IO tiles all connected through the UCI Express. That means all the whatever information CPU wanted to send to accelerator will send it as a UCIe format. So in this case, what happens is you have got different chiplets. This is one chiplet for you. This another chiplet. This another chiplet. Another chiplet. So you are just interconnecting all of these chiplets into one package. And this could finally interface with the external components through CXL and PCI Express and DDR also. This entire packaging is possible. Let's now take one more question. UCIe does credit management. ACNAC, I don't remember seeing it. I did not see that, but let me confirm. I'll confirm this in next session. I'll confirm in next session because I haven't seen anything like flow control packets. Maybe it's possibly it is happening at it is done at protocol level. It is done at protocol layer level. Okay, but I haven't seen a die to die adapter level. I mean, hasn't haven't seen at D2D adapter layer. So if it is done at protocol layer, I will just confirm that part. Uh, it can also be used for off package interconnect. What is off package interconnect? You've got one package, another package, which is, both of them can still be connected through UCI Express. Till now we talked about one chiplet, that are connected through UCI Express. Here you have some set of chiplets connected through UCI Express. You can connect these two also through using UCI Express. That is what we are calling as off chiplet, off package interconnect. UCI retimer. So in those cases, we use UCI Express retimer, may be used to extend UCI Express connectivity beyond the package using off package interconnect. Examples of off package interconnect include electrical cable or optical cable. You can even use optical cable or any other technology to connect the packages at rack and pod level. The UCI specification requires retimer to implement the UCI interface to the die that it connects on its local package and ensure that flits are delivered to the remote UCI die interface on a separate package following UCI protocol using channel extension technology of its choice. So there is a specific requirement that need to be followed when you are doing the off package interconnects. Okay, so this is an example of how this could be done, where you have got uh, the UCI enabling a long reach connectivity at the rack and pod level, where you got uh, the different elements connected. Some compute nodes are there here. Okay, some memory and accelerators are implemented here, and all of them connected through the UCI Express link. I mean, from this memory pool to different elements of this interfacing could be connected through the one package, another package. This could also be interconnected through the CXL package, UCIe connection. So basically CXL at rack level connected using any long reach media through UCIe retimers on the package. I mean, if at all you wanted to do CXL long reach connections, okay, that could be connected through UCI Express, this point to this point. Typically the standard convention is to connect it through CXL. Okay, that is how CXL technology has been developed. Now that can be replaced with UCI Express link. You can connect them through UCI Express by using the retimers on the package. You will use retimers in between so that it will adjust the timing again. Whatever skew anything, it will adjust. That is why retimers are used. Then you can pool all of them and you can interconnect them through CXL switch. Then they all can be interconnected them through UCI Express or even PCI Express, CXL, anything, they all can be done. Next. Okay, let's take one more question. I mean, I was in mute, sorry. It doesn't include any encryption. If at all encryption is required, it is responsibility of the protocol layer level. The protocol layer needs to take care of it. What is UCI Express is doing technically is, whatever information you wanted to convey from here to other chiplet, it is just acting as a medium to that to the other chiplet. That's all. So the definitely die-to-die adapter layer, physical layer don't have anything to do with the encryption. I think that is where coming to this question, how the clocks and reset handle chiplets. Okay. I think whole package will have one common set of clock and reset logic, right? Will be driven by common set of clock and reset. That is one thing. And anyway, during the initial link initialization, those will be handled. Those are handled. The synchronization and all those things will be handled during the link initialization and training. Next. Okay. Let's now discuss about some packaging options. There are three packaging options. One is standard package, one is advanced package, one is UCIe 3D package. See, these packages are given to cover the vendors can have different options. If they want lower cost, they can go for 2D packaging. When they want best performance, they can go for UCIe advanced package or 3D package. So to choose between the cost and performance, they have given different packaging options. Okay, let's now talk about standard packaging option. This is used for low cost, long reach, that is 10 millimeters to 25 millimeters. That means what? From one bump to another bump, the distance can be up to 10 millimeters to 25 millimeters when measured from bump on one die to connecting bump on the remote die. This is one die, this is the remote die. So this bump can be anywhere from 10 millimeter to 25 millimeter. Okay, that is a long gap, right? Long distance actually. It's like we are talking about 2.5 centimeters. Okay, using traces on the organic package or substrate, while still providing significantly better bit error rate characteristic compared to off package SerDes. What all the speeds this standard package supports is 4 gigatransfers per second, 8 up to 32 gigatransfers per second. That means from here to here you are able to send at any of these rates. The bump pitch can be 100 micrometer to 130 micrometer. That means gap from one pin to another pin can be this gap. Okay, channel reach 10 millimeter to 25 millimeter, long reach. Okay, bit error rate targeted is 1 out of 10 to the power of 27, 1 out of 10 of 15 based on the speeds. Now, talking about advanced packaging used for performance optimized uh, applications. Consequently, the channel reach is short. I mean, it is less than 2 millimeters. The gap only less than 2 millimeter when measured from bump on one die to connecting bump on die. The interconnect is expected to be optimized for high bandwidth, low latency with the best performance and power efficiency characteristics. Here, these are the speed supported. Bump pitch is from 25 micrometer to 55 micrometer. The gap here. Channel reach is only 2 millimeter. That is the distance between one bump to other bump. Bit error rate is like this. Okay. So how the packaging is done. You have package substrate, silicon bridge is there. Inside that you have got different connections from one die to another die. This is the advanced packaging interface. It shows few more other packaging options. The only difference is they have added something called as interposer. See, instead of doing it in the package substrate, they're putting something called as interposer. Inside the interposer, they're connecting die 1 to die 0. One more type of packaging is you have got, instead of interposer, you have got fan out organic interposer. In that, they are doing the connection. I mean, fan out organic interposer. In that, they have put a silicon bridge. In that, they're connecting. So these are the different types of packaging options that are available. Okay. Then we have a third type of packaging, what we call as 3D packaging, where, as the name itself suggests, it's a three-dimensional packaging where uh, through silicon vias, this is called as TSV, means through silicon vias. Through that, they are connecting one bump to the other devices. I mean, it's a vertical stacking. Basically, you're stacking the devices vertically. See, one die is connected to the another die through a vertical stacking. Okay. It supports up to 4 gigatransfers per second. Bump pitch is less than 10 micrometer, and channel is 3D vertical. Okay. Bit error rate is expected to be 1 in 10 to the power of 27. Uses two-dimensional array of interconnect bumps for data transmission between dies, where one die is stacked on top of the other. See, dies are stacked on top of each other. Next. So this is a brief about it. Uh, Let us quickly talk about the different UCIe components. Then we'll end the session. UCIe components. UCIe functionality is implemented in 3 layers. As I said, protocol layer, the die-to-die adapter layer, and the physical layer. The protocol layer is responsible for providing the flit information to the die-to-die adapter in the PCI Express, CXL, or RAW format. The die-to-die adapter is responsible for arbitration and multiplexing logic wherever it is applicable, uh, taking care of CRC calculation and doing the retry, link state management, and the parameter. Okay, and definitely you don't see the credit management, flow control credit management is not there here. The physical layer is responsible for link training, lane repair wherever it's applicable, lane reversal, scrambling and descrambling, sideband initialization and sideband transfers, and it offers analog front end. It also does clock forwarding. Clock forwarding means generating a separate clock and sending it to the other die. UC Express is a layered protocol with each layer performing a distinct set of functions. Okay. Protocol supported in UC Express for enabling different applications. Like it supports PCI Express, CXL, and inside that there is some RCD, RCH. I mean, root connected device, root connected host. Few such things are there. They are not supported. Streaming protocol is also supported. Offers a generic modes for user-defined protocols to be transmitted using UCI. I mean, any protocol can be transmitted. There is one more thing called as management transport protocol. It's a end-to-end media independent protocol for management communication on the UC Express management network within manageability architecture. So we'll discuss what is management transport protocol as we go forward. It's a some independent protocol which is completely different from this protocol. I mean, it enables direct management interface between one die and other die, which is completely different from any of these things we have discussed. Okay. For each protocol, different optimizations and associated flit transfers are available to transfer over UC Express. See, depending upon whether it's PCI Express, whether it's CXL raw format, there is an optimization that has been done. I told you, right? So the UC Express don't need same level of CRC and forward error correction as in other protocols. It does optimization of the available things. So it utilizes the same flit bytes for sending more information. UCIe management transport protocol can be encapsulated for transport over sideband or UCIe main band. I mean, this management transport protocol can be sent on any of the bands. Let's briefly talk about die-to-die adapter layer. The die-to-die adapter layer coordinates with the protocol layer and physical layer to ensure successful data transfer. See, its responsibility is to make sure that the whatever information it need to be sent to the other die successfully. It minimizes the logic and the main data path as much as possible, thus providing low latency optimized data path for protocol flits. See, what is done is there is a sideband which is used for all the sideband communication. So the main data path is only for sending the protocol flits. When transporting CXL protocol, arbitration mux functionality required for multiple simultaneous protocol is performed by the D2D adapter. See, earlier this functionality was implemented in CXL. Coming to UC Express, that functionality lies with D2D adapter. For options where raw bit error rate is more than 10 to the power of minus 27, a CRC retry scheme is provided in the UCI Express specification for PCI CXL, which is implemented in D2D adapter. See, the wherever you need some error recovery, right? That is CRC and retry mechanism implemented in the die-to-die adapter. The die-to-die adapter is responsible for coordinating higher level link state machine, and bring up. Protocol options related parameter exchanges with remote link partner. When supported, power management coordination among the remote link partners. They all are done as part of the D2D adapter. Now coming to the physical layer, it is divided into two parts. One is the physical layer logical part, one is the electrical. Logical physical layer, electrical physical layer. Okay. And then you have got sideband lane. Okay. It is responsible for link training, lane repair, lane reversal, scrambling, descrambling, sideband initialization and transfer, analog front end. Analog front end means the circuitry for transmitting and receiving the analog signals, and the clock forwarding. The UCIe main data path on the physical bumps is organized as a group of lanes called as module. See, whatever main data path is there, that is grouped as lanes called as module. A module forms atomic granularity for structural design implementation of UCIe AFE. I mean, you can have multiple modules being connected. A given instance of protocol layer or D2D adapter can send over multiple modules where bandwidth scaling is required. That means what it is telling is you can have multiple band connections. I'll just show you one example. You can have a scenario where uh, different configuration where you have only one module configuration. Here you see one die to die adapter, one phi logic, and one this one. That is single module. You can have another connection where you can have multiple modules also. This is also single module only. The only difference is, since it is standard package, we have to use 16 lanes or 8 lanes. In case of advanced package, you have to use either x64 or 32. This is about standard package. Then coming to multi-module package, you see you have got two modules. Module, another module. So what is the advantage? Can you tell me, what do you think the advantage we get out of it? The advantage you get out of it is you are able to send the data with double the bandwidth, right? Because you have got dedicated tracks for everything, dedicated sideband, main band, everything. You are able to get the double the bandwidth by using the, for the same protocol stack, same this thing, you are able to get the double the bandwidth. You can even have four. No, no, it's not two separate chips. It's between same chips, but it provides you double the bandwidth. Here you are getting four module configuration. So like this, various things are there. There is only one thing called as sideband only configurations are there. We'll discuss about all those things in the next session. I mean, what is the advantage, how the protocol layer differs for them, all those things we'll discuss in the next session. So this is a uh, brief introduction to UCIe Express. Now if you have any questions, we can go over that. Otherwise we are done with the theoretical part of the today's demo. Let me take one question. Can we have PAM4? No, we don't use PAM8, PAM16 because it is at our the voltage levels we are working at. PAM8, PAM16 are not possible, so they are not used. So the standard we use is PAM4 in CXL 3.2 and PCI Express. No, the problem is, one more thing you need to understand is, when you come to UCIe Express, the PAM4 is redundant, is not at all relevant, because the UCIe Express doesn't use the technology at all, doesn't use the PCI Express or CXL link layer or physical layer. It uses completely different stack. The UCIe Express has its own die-to-die adapter and physical layer, which is completely different from PCI Express. So technically what it's doing, it is taking the PCI Express packet information from the protocol layer, it is adapting, converting into different format, it is giving it to its own, which is being sent to the other one. Hence, here PAM becomes redundant.
Srinivas, can I have a question?
No, no, 1 second. But if you ask me, then why they are talking about Flit? Then if you ask me why they are talking about Flit, the reason they are talking about Flit is because otherwise, if you completely transform the information, it becomes a different. It becomes inefficient, right? They didn't want to change the packet structure. They want to retain the similar kind of structure and make the transmission more efficient. Yeah, Srinivas, please ask question.
See, above the protocol layer, can we see all the three layers of PCIe implemented and packet is coming out, and that packet is coming to the protocol layer? Can we see that way?
No, 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 no. See, that's what I'm telling. When you say all the three layers means what? You mean all the
Above the
three layers
protocol
of?
layer, above the protocol layer,
Yeah.
can we say we have PCIe all the three implemented and the packet is
No,
coming
no,
out
no.
and
They
the
won't be
packet?
there. Only, actually speaking, only protocol layer of the PCI Express will be. See, the protocol layer of the PCI Express maps to the protocol layer of UCIe. Okay, the link layer, maybe link layer, possibly. Okay, link layer should be there, but physical layer is definitely not implemented.
When you say protocol layer, it's a transport layer, transaction layer, right?
Uh,
You're talking about
yeah, transaction layer. Sorry, yeah, transaction layer.
transaction
Physical
layer.
layer of
Okay,
PCI Express is not at all implemented, not at all considered.
okay, okay. I think probably we may want to capture this as a picture so that people will next time will see, right? It will be easy to understand.
Yeah,
This
definitely.
as a,
I'll do that. I'll definitely include all these things.
because
Uh,
pictures speak volumes. It's people remember pictures better. Yeah, just a request.
no, no, no. I didn't had time last week. I was busy with
That's
some
okay.
other
That's
SOC
okay.
training.
No.
This week
Please
I
go
have
ahead.
time.
Don't worry. No. But whenever you want to do it, show that as a picture so that people can remember that for a longer period. So easier.
Definitely, I'll take this input. I'll make sure that I will put more of relevant pictures. Yeah.
Sure. Thank you.
Any other questions? Okay. Since it's chip to chip, or it's a die to die, they wanted to make phi simpler. Okay, focus more on performance in terms of latency throughput, support multiple protocols at higher layers. Yes, see the fact that die to die, the trace length is much smaller than PCI Express or CXL. See, generally these PCI Express and CXL tend to be in larger, right? Multiple, I mean, upside of centimeter also, centimeters, right? Trace length of the connections. Whereas die to die will be much smaller. You saw some time back that it was 10 to 25 or 2 in case of different packaging styles. Because of that, the problems that we face in PCI Express and CXL won't be there in UCI Express. Hence, it gives provision for making the physical layer simpler. That is where they're able to utilize that. They are able to get the performance and in terms of latency and throughput out of it. Does it answer your question, Sandeep? Okay, Manikanta, let me take your question. They wanted to make um, okay, let me take this question. They wanted to make uh, phi for D to D. The actual phi is not intended for. No, can you please repeat your question, Manikanta? Can you just repeat your question? They wanted to make phi for D to D. It's not like phi to phi. Essentially, you want to send some flit from one. Yeah, yes, I would say correct that only. Yeah, die to die will have a flit. Okay. Oh, okay, fine. I think if you answered, then it's fine. Yeah, I think you are just answering the question for Sandeep. Then it's fine. Yeah. So that completes. Uh, yes, it supports it, Sandeep. Yeah, I'll take that question again. I'll write here. One die at 28 nanometer technology, another die at 2 nanometer technology node, they can be connected through UCI Express. It is supported. Only thing is, whatever is the packaging options, they have to follow that standard packaging or whatever, right? Those packaging thing they have to follow. Then, as long as they have that packaging options followed, then they can be interconnected. Next, one question: does off-chip die package UCI Express? How it differs from in terms of architecture of die package? No, it is same. See, the UCIe layers are same. The only thing that you do is one package, another package, off package when you are connecting. In between, you use the retimer. That's all. Somewhere here, you'll use the retimers so that whatever skew that gets developed, it will fix that. Any signal loss, anything, it will fix it and again sends it. Otherwise, it's all same. You still have physical layer here. You still have physical layer. It just, fixes any noise or any signal loss, attenuation, sends it. Otherwise, it's all same. Architecture wise, it's all same. Is that clear, Manikanta? Uh, any other questions? Okay, if you don't have any other questions, the next session will be on the coming Saturday. Okay, that will be today's 9th, right? So 16th of August will be the next session. If you are okay, we can even have 15th August also.
I will complain, Srinivas Reddy, if you have it on 15th.
Yeah,